Yeah, welcome everybody. Thank you for finding your way to this short video summary or teaser of the recent new preprint of Emmanuel Jacob, Benedikt Janel, and myself about subcritical annulus crossing in spatial random graphs. Let us start with the framework. So we build a graph on the points of a stationary point process of some intensity lambda, and then we add edges in a way that preserves stationarity, but that also only attaches in expectation a finite number of edges to each vertex. So in other words, we have a translation invariant sparse graph, but still there could be a lot of interactions, a lot of correlations between the vertices or the vertices and edges or between the edges. And the standard question in percolation theory is then give me such a model, and then whether there exists a phase transition, so a critical intensity lambda c, such that there cannot exist an infinite connected component in this graph whenever my intensity is smaller than this intensity. And rather than studying this question, we study an alternative phase transition called lambda hat c that goes back to Guret in this context. And here we ask, is it possible to prevent larger and larger annuli to be crossed for small intensity? So here in the picture, you see an annulus of radii r and 2r, and we find a vertex in the middle ball that goes over the annulus by a path and connects itself with this path to a vertex outside the large ball. And the question is, can we prevent this for small enough intensities? And to answer this question, we somehow have to gain control about the long-range effects of the models. And the long-range effect can either be there because of there are long edges. So a long edge is an edge of length r, where one of the end vertices lies in the ball BR. And we don't want to have such long edges because a single such an edge could cross the annulus alone. And the other way there could be long-range effects is to consider two, let's say, annulus crossing events of size r at distance roughly r, and because they could help each other because there are long-range interactions between the vertices and the edges, and we don't want this to happen too strongly. So if I increase distance and size, they should become eventually independent in the limit, or in other words, the covariance that both of these events happen should go to 0. And if I have this now actually uniformly for small intensities, then indeed lambda hat c is positive. So, but I really need a uniform condition here, because we allow so many correlations that reducing the so establishing the absence of long edges, let's say, but then reducing the intensity slightly to take care of the other interactions, then gives me long edges apparently again. So we really need this absence of the two long-range effects uniformly. And if we have this, lambda hat is positive. And moreover, if we actually have polynomial decay of the both long-range effects, then we also have polynomial decay of the defining probability. And if we consider a bit more independent model, so we say disjoint regions are are independent. So the covariance is actually 0 for in these situations. And conditioned on the vertex set, edges do only depend on the end vertices and not on surrounding vertices. Then lambda hat larger than 0 is equivalent to not having long edges for some intensity, say 1. So this gives me a situation where either all large annuli essentially are crossed with a single long edge, or they are impossible to be crossed for small intensities. What else can you do expect? Many examples where we apply this. For instance, we discuss in great detail the weight-dependent random connection model, and some generalizations of it, which is a yeah, um, lively field of research at the moment. So many people study the weight-dependent random connection model at the moment, and we try to add something here. And we calculate precise tails of the involved long-range effects and uh, covariances, and relate these tails to findings of other recent articles on finding there also to connectivity events. And then we provide examples how you could choose a more correlated vertex set than, let's say, a Poisson point process based on lattices all in the continuum, both as possible, and give examples for that, and also how to control the correlations there and prove the required mixing. And then we give some examples demonstrating that the assumptions cannot be weakened, so that we really need this uniform assumptions on the mixing and the long edges probability. And then finally, of course, there are proofs. Yeah, I hope I could motivate you to have a look in our paper where we make this in detail and also much more precise than I just told you here. And thank you for your time.